On to the trapezoidal rule for numerical integration. We saw that the left point rule and the right point rule, they can be used, but they might not give always satisfying answers. A better method now is the trapezoidal rule, and this is of course based on a trapezoidal construction. So again, one of these images where you have a curve and you want to find the integral, so the area under the curve. And now instead of approximating this by rectangles, we approximate it by trapezoids. So here's one example. Here I'm plotting the trapezoid A1, and I take this area as an approximation for the area under the curve. Okay, and then I take the next one maybe here, and I take this area, and I take the next one maybe here, take this area, and so on. So I again split everything into sub-intervals as we have done so many times, but now I look at the areas of these trapezoids. So what is the area of a trapezoid? Here we go. So the area of this ice trapezoid right here, okay, is delta x, which is the width, divided by 2, and then we take the height, oh I forgot a bracket, we take the height f of xi minus 1 plus f of xi, and then take kind of the average height times delta x. If you want to write this in terms of y, so then here's the same formula in terms of y. And then for the integral, we sum up all these trapezoids. So then this one would be the first one right here, this one would be the second one, and then on so on, and this one would be the last one. And then you see between the first one and the second one, you have the term y1 appearing twice. It appears here and here also. So I can combine this into a 2y1. And same for y2 appears twice, and so on. Only the first one y0 and the last one yn appear only once. But they do appear. We are not forgetting any of the points, like we did for the right or for the left point rules. Okay, so then let's do this for this example here. So I take just the previous formula for the trapezoid rule, but now I write it in terms of r, not in terms of f. And so I sum up the first point, twice the second point, twice the next point, and so on. And then the last point is counted only once, but they are included, which means now I'm using information from the whole thing. So this is used for T6, and then I get 26.257. And that seems to be right in the middle of the other two values, giving us a very good approximation. There was another example with the integral of sine square, right, or sine of x square here. Integral from 0 to 3 sine of x squared dx. Again, I use the trapezoidal rule, and here I write it down again. Okay, I take delta x over 2, and then the first point and the last point I take once. All other internal points I take twice. All right? And so let's make a little table where we have then the index I goes from 0 to 6. The point xi is incremented in steps of a half. The value of sine x squared is written here, etc. Yeah, and so we just take all these values here and sub them appropriately into this formula, and then we get the value 0.6415. All right, so let's compare this to Wolfram alpha. I don't know if you have talked about Wolfram alpha. Many of you know Wolfram alpha quite well. If not, then let me just show this to you just quickly. So here is Wolfram alpha. You just type Wolfram alpha in your browser and then you find it. And for example, here you can just enter the expression you're interested in. For example, integrate sine of x squared from 0 to 3. And what do we get? We get 0.77563. We also see how the curve looks like, and we see that we have positive areas and negative areas, right? So then the sine areas, and you have to do those plus and those minus. Let me summarize. We discussed 3 methods for numerical integration: left point rule, right point rule, which is really nothing else than the Riemann sum, and then the trapezoidal rule, which seems to be quite good actually in numerical integration. There are many more, many more, but we will not discuss the other ones in this class. Yoo-hoo! Yoo-bee! Yoo-hoo! Hey, I catch ya! Where are you coming? Gotta see! Yoo-hoo! Oops.